to computer vision. And so here, what we're going to do is recognize these clothing items. This is a famous problem. These are little black and white images, 28 by 28 pixels, and you can sort them into categories: t-shirt, trouser, pullover, dress, coat, sandal, and so on. And the data comes labeled, so you know what the right answer is for all that data. So what you do, the typical thing you do, we're going to do the same thing, although we are going to do something which is in fact a little screwy. What we're going to do is feed in every pixel as an independent bit of data. We are not going to preserve anything about the spatial relationship of the pixels. This is arguably not the right way to do it, and not the way your brain does it. Your brain and eye does it by detecting edges and passing an edge and stuff up for higher levels of processing, and that might be a better way, but what we're going to do here is this way. We're just going to feed in all the pixels, which are 768, as independent pieces of data, and then pass them through the same kind of processing, some hidden layers, and then have 10 output layers. 10 output neurons, and the signal in the output neuron will be the probability that it's in one of these categories. So I take the input image, I feed all the pixels in, then I have a hidden layer to do the processing, and then I have an output layer, and the signal that appears here measures what the probability is that it's a coat, a sneaker, a bag, or whatever else. So there's the code. Now what this code does is break the data into training sets and test sets, and this is how you do it. If you have a bunch of data, you don't train on all the data you have. What you do is you take part of that data, like 80%, and train on it, and then you take the part that the model has never seen before, typically something like 20%, and you test it on that to see if your model is actually learning the trend of the underlying data. You can make mistakes. There can be problems where your data learns the wrong thing, or where your model learns the wrong thing. So let me clear this out and put in another one. All right. So this is going to input the training images, called fashion MNIST, and it's going to just set them up. And here's the model. I have 28 by 28 pixels coming in. I'm going to flatten it into one flat layer of 28 squared, then 128 hidden neurons, and then 10 output neurons. And so it's ready, and it looks like this is in fact going to do the fit and the evaluate. I think this is going to do everything. Thought it was, there's downloading the data. There it is. It's going to train in 5 epochs now. So the first epoch runs, and it's taking a while, like maybe 10 seconds per epoch now, with a more complicated model. And see, here's the loss, is the measure of the error. So 0.6, and with each step, the loss should go down, 0.3, 0.38, 0.34. Good, so it is optimizing. It's making the loss smaller. All right, and so when you're done, here's the results. It has printed the evaluation on the test images and the test labels. So this means 87% accuracy on the test images. Now let me go back to my instructions and make sure I'm interpreting that output correctly. Yeah, there should be 2 numbers, an accuracy here and an accuracy there, which would be 89 and 87. That's what I expected. And yeah, I see, it's just wrapped around. Oh, here we are. Nope, that's not it. Right, here's the 88 and the 87. All right, I expected 89, and I think I did. Here's epoch 5, yeah. So this is the 89% on the training set. So it has learned to get 89% of the training set correctly classified, and the test set, it only gets 87% of them correct. That's what you expect. If you have a well-trained model. It's almost as good on the test set. Now, I think we got an example here for overfitting. First, let's take a look at the results for the first 20 images. All right. So if I go here. All right. So here's the first 20 images. And what I've done here is I've just made, I gotta get this thing to shrink. Okay. These are 10 columns. This is the probability that it's number 0, number 1, number 2, up through number 9 type category. And so here you see the right answer. The right answer is category 9, and the model gave it a 90% chance of being a 9. So it did a good job in that case. Here's 2, and it's mostly a 2. Here's 1 and 1. If you look for ones that are low, this one's really a 6, and it's 0, 1, 2, 3, 4, 5, 6. It was only 62% confident. If you look down here, you'll find ones where it failed, because it does fail like 10% of the time or so. And like this one here, 54 and 45, the right answer is 4, but it got it wrong. It decided it was a 2 with a higher probability than a 5. Now here I printed from 0 through 19, so 19, this is number 17. Number 17 is one it got wrong, so it would be good to look at the actual image for that. So let's view the images. And I'm going to do test image 17, because that's one it got wrong. 0 is one it got right, and 17 is one it got wrong. So here's one it was able to correctly classify, and this is the one it could not correctly classify. It couldn't tell if this was a 2 or a 4. And options 2 and 4 are there. 2 is a pullover, and 4 is a coat. So it couldn't tell if that was a pullover or a coat, and I don't think I could either. I'm not sure I know what the difference is between a pullover and a coat. I'm ignorant in the ways of fashion. So it's reasonable. It's doing a job like a human would, even though it's treating all these pixels as independent data. It's not retaining anything about the relative position of the pixels. It has somehow learned to do a pretty good job classifying that data. All right. And so that's what I wanted to show you on that one. And I think I'll just demonstrate one more of these to get you folks started.